viewers, welcome to CEC lectures. Myself Dr. Preeti Ragwani. I am from Department of Computer Science, Aribhat College, University of Delhi. So presently we are going through our series of advanced data structures and algorithm, and in our previous lecture we looked into the maximum flow problem. Today's topic is a different module which is named as Fibonacci heaps. Now Fibonacci heaps, or let us say only heap if I am talking about, let us try to recall that what actually a heap is, what kind of data structure is this, and then I will take you to Fibonacci heaps as well. So heap, if you remember, that is basically a nearly complete binary tree that can be arranged either in the form of a max heap or in the form of a min heap. So in max heap you have the parent is at least greater than equals to both of its child, and if it is kind of the reverse of the condition, that parent is less than equals to both of its child for each and every subtree, then this is kind of a min heap, but it is a nearly complete binary tree. Now when we talk about Fibonacci heap, so Fibonacci heap is basically we can say it is a collection of trees. What kind of trees I am talking about? The trees that satisfies the minimum heap property, that is nothing but that the key of child is always greater than or equals to the key of the parent. That is what minimum heap property is, and Fibonacci heap is a collection of some such trees which satisfy the minimum heap property. So that means if I am talking about a minimum heap thing, this implies that the minimum key is always at the root of one of the trees. Now when we compare this Fibonacci heap with one of its kind of a different version of a heap which is nothing but the binomial heap, we can comment that the structure of Fibonacci heap is more flexible as compared to binomial heap. Binomial heap is rigid in terms of the structure, but binomial heaps we have not studied because that is we can say kind of out of scope of this particular course. But Fibonacci heap, yes, that is actually an important data structure because of its kind of flexibility. So the flexibility allows some operations to be deferred till a particular time, or we can say that the flexibility allows some operation to be executed in a lazy manner, postponing the work for later operations. So Fibonacci heap is flexible while binomial heap is actually we can say rigid in terms of the structure, and the flexibility is also lesser in binomial heaps but more in Fibonacci heaps. And if we talk about shape of these min heap trees, then I will be able to say that the trees do not have a prescribed shape, and in the extreme cases the heap can have every element in a separate tree. So one element consisting of one tree, or we can say one tree is having only one element, and so many such trees implemented together or joined together with the help of a list, how that I will be showing you in a while. So that is known as actually Fibonacci heap. So whenever we talk about a heap, there is the underlying data structure which is used for implementation of heap is priority queue. So basically when we talk about the data structure used for implementing priority queue is type of the heap data structure, but here we are talking about several improvements over the traditional binary heap which we have seen in our normal algorithm course, or not the advanced algorithm but the design and analysis of algorithm course. We have seen binary heap in in a detailed manner, and this is also having several improvements over this binomial heap data structure, some of which I have just mentioned, that in terms of structure and in terms of flexibility of the operations to be carried out. Now when we already have our binary heap version, then a binomial heap, then what is the need for these this a new kind of the data structure which is Fibonacci heap. So, Fibonacci heap is going to give you some advantages over binomial heap and the traditional binary heaps. So, there are two different we can say differences, or two lines of differences between Fibonacci heap and the binomial and traditional binary heap. So, one is the this Fibonacci heap data structure is more kind of we can say is more fast. That means it is amortized running time for some of the operations, which operations for insert, for merge and for extract min operation. The amortized running time for these operation in case of a Fibonacci heap is kind of we can say much lesser as compared to the other heap data structure. So, because of this less amortized time, Fibonacci heap is one of the most efficient data structure for for the scenarios where these operations, which is the insertion operation, insertion of a key into a heap, or merging of two heaps, and also extract min operation, which is a very common operation. So, if these operations are to be kind of executed repeatedly or executed frequently in an application scenario, so Fibonacci heap is going to be the kind of most important or most suitable structure here. So, running time of these operations in Fibonacci heap is order 1 for insertion, then for extract min it is going to take order log n, and order 1 for the merging thing. But please remember that these are amortized time complexities, these are not asymptotic time complexities, and I hope you understand the difference between the amortized and asymptotic. So, if you want to refer more about this amortized time complexity, please refer to the lecture of amortized time complexity which was included in design and analysis of algorithms series. So, when we say or when we consolidate the information which we have seen till this point, we can say that Fibonacci heap is actually a collection of trees in which each tree is a heap, ordered multi tree, meaning that each tree has a single node with its children arranged in a heap ordered manner. Also, the trees in the Fibonacci heap are arranged in such a way that the root node with the smallest key is always at the kind of we can say front of list of trees. This kind of arrangement is also possible when we talk about Fibonacci heap. So, there were kind of two purposes what I was talking about. So, one is we have thrown a light on the amortized time complexity. So, amortized time complexity for various operations is lesser as compared to other heap structure. So, that is one advantage of Fibonacci heap. Another purpose or another advantage of Fibonacci heap is that it supports a set of operation that constitutes what we call as a mergeable heap. So, mergeable heap, all the operations which are allowed for any data structure of mergeable heap type, your Fibonacci heap is going to support all that set of operations. So, we will be definitely looking into all those set of operations, and we will be also looking into their amortized time complexities. But before going into the details of this, let us try to recall that what we have completed till now. So, till this point we have seen that we have binary heaps, then we have binomial heaps, and then we have Fibonacci heaps. All these are heaps, basically a nearly complete binary tree, a nearly complete tree, and here in case of binary heap, that is going to be a nearly complete binary tree. In case of binomial heap and in case of Fibonacci heap, the case is going to be different because they do not claim to be only binary trees, if we say. Then why these Fibonacci heaps are required? So, one is they provide us the operations which are related to the mergeable heap data structure. And another purpose or another advantage of Fibonacci heap is that there are some operations which runs in constant amortized time, not only the lesser amortized time, but the constant amortized time. So, because of this constant amortized time, this data structure is well suited for applications they invoke, that invoke these operations frequently. So, Fibonacci heap structure wise, if we can see, it is a collection of trees where each tree is a heap ordered multi-tree. That means each tree has a single root node with the children arranged in a heap ordered manner. So, this was basically, we can say some comments or some introductory notes about the Fibonacci heaps. But as I have told you that these Fibonacci heaps supports the operations which are available, for mergeable heaps. So, first of all, let us try to look into that what actually the mergeable heap is. So, mergeable heap, if we talk about, is a data structure that supports basically 5 operations. And here what are those 5 operations? Those 5 operations are make heap, then we have insertion of a key, then we have finding out the minimum, or just traversing the minimum, or printing the minimum, we can say. Then there is kind of extract min h. Extract min h is also an operation. We will be looking into all these operations in a short while in a detailed manner. And then finally kind of union of two heaps which are h1 and h2. So, all these are mergeable heap operations. Now, let us try to understand these operations one at a time. So, the first operation which I told you was a make heap operation. So, make heap, as the name indicate, it will create a new heap and returns a new heap which presently does not contain any element, because we have not inserted anything within this heap. So, that is the make heap operation which creates and returns a new heap, and that new heap contains no elements. Now, why I am kind of insisting on the term no elements? Because this term no elements is going to help us in our amortized analysis. Then next, the operation which is about insertion operation. This insertion operation is going to take 2 parameters. One parameter is an heap pointer, we can say, or a pointer to the heap, which is the heap is h, and another one is x. So, x is an element which is to be inserted, and here the assumption is the key has already been filled into this heap h, and we want to insert that element. We will be looking into the whole pseudocode and obviously of course the analysis of these operations. Then the next operation which comes there is minimum among this h, or just passing a pointer to the heap. The minimum is, or this minimum function is going to return a pointer to the element in heap h whose key is minimum. So, the minimum element which kind of we are trying to find out. Then comes the fourth operation is extract min from this heap h. So, extract min h. So, the earlier operation was minimum h and here it is extract min h. So, in the earlier operation there was no extraction of the minimum element or the element with the minimum key. It was just kind of, we can say, printing the element with the minimum key. But here if we talk about extract min h, this is going to properly remove or delete the element from the heap h whose key is minimum, and then it will return a pointer to that element which is being kind of deleted. So, first it will not only kind of print, or it will not only find out the minimum element, it will also delete the element from the heap h whose key is minimum, and the pointer to that particular element is kind of, we can say, sent back as a return value. In this line of mergeable heap operations, the next operations which we talk about is union H1 and H2. So, here H1 and H2 are basically two heaps, and union H1 comma H2 is going to create and return a new heap that contains all the elements of heap H1 and H2. So, whatever elements are available in H1 and whatever elements are available in H2, all those elements are will be contained in the union. And the important thing here is heaps H1 and H2 are going to be destroyed by this operation. So, after union there will be kind of no individual heaps H1 and H2. This is something which is to be kind of taken care of. Now, these 5 operations which I have just described, one is make heap, another one is insert, then there is minimum, then there is extract min, and finally union. These 5 operations are known as mergeable heap operations. But as far as Fibonacci heap is concerned, it is not just the kind of, what we can say, it is not just the these operations. Apart from the these mergeable heap operations, the 2 operations which are decrease key and delete, these 2 operations are also supported by Fibonacci heaps. So, decrease key, when we talk about, it takes 3 parameters. One is h, the heap, or the pointer to the heap. Another one is x, which assigns the element x within an heap h the new key value k. So, h is going to be, that element h will be given a new key k, and this k is assumed to be no greater than its current key value. So, because we are talking about the decrease key operation, then the k should be at lesser than the whatever value is that element x is presently having. After that, there is an operation which is delete h comma x. So, h again is the pointer of the heap, or is the we can say the handle to the heap, and it will delete the element x from the heap h. So, apart from the mergeable heap operations, your Fibonacci heap also supports these 2 operations. One is decrease key operation, another one is the delete operations. So, mergeable heap operations we have seen, and the dual purpose in which the Fibonacci heaps are going to be utilized. The second purpose was kind of less amortized time. So, here you can have a quick glance of what is the difference between the worst case conditions of the binary heap for various operations like make heap, insert, minimum, extract min, union, decrease key, and delete, and also the when the analysis is performed in amortized fashion, or amortized analysis is performed in case of Fibonacci heaps. So, make heap, it is having the same we can say same time complexity of binary heap, same time complexity in case of binary heap as well as in case of Fibonacci heap, that is theta 1, a constant amount of time. Then insertion in case of binary heap, as you can see on the screen, is going to take theta log n, while insertion in Fibonacci heap is going to take only theta 1. Why and how, that we will be looking into the various operations when we will take them. Then the third which comes up in line is about the display of minimum. So, both the binary heap worst case and the amortized analysis of Fibonacci heap is going to give theta 1 for both the scenarios will give you theta 1 for this printing the minimum value. Then there comes not only the printing, but the extraction or removal or deletion of the minimum value, which is theta log n in case of binary heap, which is the worst case, and in case of binary heap amortized analysis, this extract min operation is equivalent or is having time complexity order of log n. Then if you can see the three other operations, which are union, decrease key and delete. So, union in case of binary heap is going to take theta n time, while in case of amortized analysis of Fibonacci heaps, this is claiming to take only theta 1. Then when we talk about the next operation in line, which is the decrease key. So, decrease key in case of binary heap, worst case is going to take theta log n, while in Fibonacci heap amortized analysis it is going to take theta 1. So, these are the two kind of two major operations here apart from insertion operation, which are going to significantly improve in terms of time complexity if we talk about Fibonacci heaps. Then there is an operation which is the delete operation. So, delete operation in case of binary heap is going to take theta log n, but in case of amortized analysis of Fibonacci heaps, it is going to take order log n. So, this is basically the difference between the time complexity of various operations in case of binary heap as well as in case of Fibonacci heaps. Now, with this background or with this bottom line established, let us move on to see how these Fibonacci heaps actually look like. So, these Fibonacci heaps are basically a collection of rooted trees, and these trees are nothing but min heap ordered. That means each tree is obeying the property of min heap, which says that the key of a node is greater than or equals to the key of its parent. Now, here on the screen you can see a Fibonacci heap. So, here this Fibonacci heap is having 5 different trees, out of which the 2 trees are having only one element, only one node, and these are 23 and 7. Then we have one tree in between which says the root element is 3, 18, 52 and 38 are the children, and that is why I have told you that this is not a binary tree, because here if you can see in this example, the number of children for 3 is, for the element 3 is 3. So, one is 18, another one is 52, then we have 38 and 18 is having 39 as its child, while 38 is having 41 as its child. So, that way it is satisfying the min heap property. Moving further, we have one more tree which is having 17 as the root and 30 as the child element, and then finally there comes a tree in which 24 is the root, and then 26 and 46 are left and right child respectively, while 35 is we can say 35 here is the children of 26. Now, here you can see in this figure some nodes are shaded, for example 18, then 39 and the node 26. The technical meaning here is these nodes are actually marked. What do you mean by marked nodes and how it is going to help us? That will be looking into maybe in our next lecture. But here, yes, this much I can say that 18, 26 and 39 are actually your kind of the marked nodes. So, marked nodes have have a different significance here. So, 5 trees with different roots, and if you can see on the screen there is a pointer which says h dot min and it is pointing towards 3. As it is the min heap, the the lowest element among each tree is going to be on the root. And if we look into the root of 5 different trees in this figure, one is 23, 7, then 3, 17 and 24. So, the minimum element among this whole heap is going to be definitely on the root of the trees because of this min heap property. and among all the roots available, or among the 5 roots available, the minimum the element with the minimum value is having a key as 3. So, basically the H min pointer is pointing towards this. Now, if we look into some kind of technicalities that how these Fibonacci heaps are going to be implemented. So, here comes figure which is there to guide us, that in the sense that these Fibonacci heaps are basically arranged, or we can say implemented with the help of doubly linked list. So, these doubly linked list, you can notice there is a doubly linked list which is containing kind of all the root elements, and this is shown in 2 parts because of the sake of clarity. Then 18, 52, 38 is again in the form of a doubly linked list, and so on and so forth. So, here is 26 and 46, and the element 30 which is all alone as a child element in the 4th tree having 17 as its root is also in the form of a doubly linked list. So, this doubly linked list is, or even this circular doubly linked list is going to serve so many advantages as far as these Fibonacci heaps are concerned. We will be throwing a light more onto this structure, and then we will be looking into the different operations which are to be performed on these Fibonacci heaps in a detailed manner, but that is all in our upcoming lecture. Here is a list of references which is being used for the preparation of this lecture. I hope you have enjoyed one. Thank you for a patient hearing. I will see you in the next. Till then, take care. Goodbye.